sheets, they have hydrophobic residues on both sides because it's in the core of the protein. That beta sheet's in the core. It's in the hydrophobic middle of the protein. And so it's got hydrophobic residues on both sides of the sheet. If you looked at the strand, and we did this the other day, if you did the strand like this, and these are alpha carbons at every position, there's nonpolar residues at every position in the protein, both sides of the sheet. Okay? Nonpolar, 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 and so on. Okay? So you got hydrophobic residues on both sides. How are you going to put that protein in a solution with water? You got to coat it with something. What do you coat it with? What do you suppose these are? Those are something we looked at last time. Amphiphilic alpha helices. Helices that are nonpolar on this side and polar on this side. So you have a beta sheet and then amphiphilic alpha helices. And those helices are nonpolar on this side, polar on this direction. And so you get solvent, amphiphilic helix, hydrophobic stuff in the middle, beta sheet backbone, hydrophobic stuff, amphiphilic helices, and solvent. Okay? So the yellow here, the yellow shading, is the hydrophobic goo in the middle of the structure. The hydrophobic residues are the yellow here. Okay? So the backbone of the beta sheet is like this, and you have nonpolar residues, the yellow part outside of that. And then the helices cap that, and those helices are special. They're amphiphilic. They've got nonpolar parts on this face, polar parts on this face. So you go helix, sheet, helix, and there's two regions of hydrophobic stuff in the middle. Okay? Here's a case where you just have nothing but alpha helices. But if you think about it, these are all amphiphilic alpha helices, and there's hydrophobic stuff in the middle. So there's nonpolar stuff down the middle and polar on the outside, so this protein called cytochrome C prime can exist in water. All right? It's using the helices to bury the hydrophobic stuff in the middle, and yet it can still interact with solvent water. And here's another example. This is a 5-layer structure. You've got a layer of amphiphilic helices, then a layer of nonpolar helices, right? It's hydrophobic on this side, hydrophobic on this side. These are amphiphilic helices, solvent water out here, goo in the middle. So amphiphilic, nonpolar helices, nonpolar beta sheet, parallel beta sheet. Here's a layer of nonpolar alpha helices, hydrophobic goo, and amphiphilic alpha helices out there. Isn't that beautiful? It's a way for the protein to exist in water and still accommodate the hydrophobic core. So you can do the most possible hydrogen bonding in the middle, which mitigates the polarity of the backbone. So you get a hydrophobic middle, and you get amphiphilic helices on the outsides to cap it so it can interact with solvent water. Yeah?
So it seems like in this example, you're giving us all these beta sheets are non-polar. Is that kind of standard across?
And that is absolutely true for parallel beta sheets. Okay. And so we'll tell you then that anti-parallel beta sheets are different. Okay? Typically, parallel beta sheets are almost always found in the core of globular proteins. So they've got hydrophobic residues on both sides. But anti-parallel beta sheets with one strand this way, one strand that way, one strand this way, those are surface elements in proteins. So let's draw, we don't have one here, but let's draw a picture of an anti-parallel beta sheet and where it would be located. It's a really good question. I love it. So here's a protein, and we're going to have an anti-parallel beta sheet right there. It's pretty ugly, but that's an anti-parallel beta sheet. Okay, one strand goes this way, one strand goes that way, one strand goes this way. You get the idea. Okay? And then over here, maybe you've got helices or something. But that anti-parallel sheet is going to be on the surface. Right, surface vertically. That's the surface of the protein. So what do you think that beta sheet is like? It's got nonpolar stuff here and polar residues sticking out here. So these are polar residues. Okay? Polar residues on one side of the sheet and nonpolar residues on the other. And for reasons that we don't entirely understand, proteins have evolved in nature so that the Beta sheets in the middle of globular proteins are all parallel with nonpolar residues on both sides of the sheet. And antiparallel structures have evolved to be surface structures. Antiparallel beta sheets are surface structures in globular proteins, and they have polar residues on one face, nonpolar on the other. So the nonpolar side goes to the hydrophobic core. The polar part interacts with water. That is a great question. Does that make sense? That help you? Antiparallel beta sheets are surface elements in protein structures. Parallel beta sheets are almost always in the middle, in the core, with nonpolars on both sides of the sheet. Isn't that neat? It's a little thing you can always trust when you look at protein structures. Works almost all the time. By the way, in the original construction of our textbook, we got these structures themselves as paper drawings from Jane Richardson. This is when it wasn't even easy for us to do structures like this. This is way back in the mid-1980s, and we didn't have computer programs then that could display proteins so easily by computer. And so we got paper drawings of these 4 structures from Jane Richardson, and then our artists colored them to show where the hydrophobic stuff was in the middle, the yellow goo. And then we drew the planes through them. And she had not done that. We drew the apparent glass planes through the structure to indicate the layers in the structure. And then when we showed them to her, she said, wow, that's a really nice idea. She hadn't thought to do that. But she had written a whole review article about layer structures in proteins. We added the glass panes, and we were the first ones to do that. She thought that was a really nice addition to displaying these proteins. And so it's something we actually got from Jane Richardson herself. She's a lovely lady, by the way. If you go to apply at Duke, anybody thinking of going to Duke? If you get an interview at Duke and they say, who would you like to talk to? Ask to meet Jane Richardson. First of all, they'll be knocked over that you know who she is and that she's there and that you know her story of being a world-famous protein expert with no PhD. And secondly, she's one of the nicest people you'll ever meet. She's a very sweet lady, and she's older now, but I'm sure she'd be happy to talk to you. So try to meet Jane Richardson. She's incredible. So anyway, all right. Now, to finish off the structures of globular proteins, we say that most globular proteins belong to one of 4 structural classes, and we'll go real quickly through this. There are all alpha proteins, where alpha helices predominate. We're calling them all alpha, but they're not totally. And there are proteins called all beta proteins, where beta sheets predominate. Then there are alpha/beta proteins, where helices and sheets are mixed together. And then there's alpha plus beta, where there's an alpha domain and a beta domain. So we'll just show you real quickly that there's structures like this. There's the all alphas at the top, including one of my favorites, the cat allergen, up in the upper right corner. I'm deathly allergic to cats. That's what the cat rubs off of its fur to make you sneeze and cough if you're allergic to cats. And here's the all beta structures that we pulled out. And these are alpha/betas, and these are alpha plus betas. And no big deal about knowing the difference, but just know that people classify proteins. And then we'll go on to molecular chaperones. This is a really good story about what are called heat shock proteins, and you might be interested in how that came to be. How did we come up with the idea of chaperone proteins? It was imagined long ago that there might be a need for other proteins to help certain proteins to fold, but nobody had identified them. And then one day, people were doing an experiment that might have been considered pretty silly. They were looking at the growth of bacteria at different temperatures. So they grew the bacteria at room temperature, and then they grew them at 37, and then they tried 40 degrees, and then they tried growing them at 45 and 50 and 55 and 60. And as the growth temperature got higher and higher, the bacteria made a certain family of proteins that they didn't know about before. They were made in such small quantities at room temperature that nobody had observed these proteins before. But when you grew the bacteria at 65 degrees Celsius, which is really warm water, by the way, they found that the bacteria made extra proteins of a certain sort. And these turned out to be proteins that were helping the other proteins in the bacteria to fold and stay in their normal conformations, normal states. And they're now called chaperone proteins. And since these were discovered in experiments where you shocked the bacteria by growing them at high temperature, these are now called heat shock proteins universally. And HSP stands for heat shock protein. And then 60 or 70 mentions the molecular weight, if you will. So that's a 60,000 Dalton protein. That's a 70,000 molecular weight protein. But they are heat shock proteins, as it turns out. Proteins that chaperone for other proteins, and they help other proteins to fold. So we'll talk more about these down the road. We won't say much here. But this part is really important. Intrinsically unstructured proteins. We've mentioned these before. It turns out that many proteins exist normally in a partially unfolded state. They're called intrinsically disordered proteins or intrinsically unstructured proteins. So IUPs or IDPs, either one is good for this. And they don't possess uniform structural properties until you bind them to something else. And it turns out that these proteins have a near complete lack of structure and therefore high flexibility. And they adopt well-defined structures in complexes with target proteins, things they evolved to bind to. And here's one of the most interesting things. They're characterized by an abundance of polar residues and a lack of hydrophobic residues. And you know already what that would mean. Imagine the strand of spaghetti is sitting there, and all of a sudden we take away its nonpolar residues, and we say most of it's polar, okay? What's going to happen? There won't be any hydrophobic collapse. The protein won't be able to collapse and fold it into a well-defined structure, so it stays unfolded until it meets a target protein, and then it sticks to that. And you'd think, well, what a silly thing to do, because why can't it have a structure to start with? But here's the wonderful thing about that. That unfolded structure can bind to this target protein, or this target protein, or this target protein, or this target protein, or anything like that. The unfolded protein can bind to multiple targets. And we're going to show you in a minute a protein that actually binds to hundreds of target proteins, and it's a tumor suppressor protein. Why didn't we know about these 40 years ago or 50 years ago? The quick story is that the protein structure people were doing experiments like this. They were looking for proteins to determine structures for, so they'd get 100 different proteins, and they'd try to get them all to crystallize. They'd have little vials or solutions for crystallizing this one and crystallizing that one and crystallizing this one. And some of them crystallized and made nice crystals, and they got structures determined from those. And the other ones didn't crystallize, so they said, well, those are just wasted, throw them away. And they ignored them. And this is like the joke about the drunk looking for his keys on a dark city street. You know that one? So the drunk is wandering around like this under a lamppost, and another fellow comes up and says, what are you doing? And the drunk says, well, I'm looking for my keys. And the other guy says, well, where'd you lose them? Drunk says, way down there. The fellow says, why are you looking here? And the drunk says, there's more light here. And this is what the protein structure people were doing for years. They were only looking at the proteins that crystallized. They weren't asking any questions about the stuff that didn't crystallize, where the most interesting structural things were. The proteins that didn't fold, that didn't make crystals, now turn out to be the most interesting ones. And here's the other nugget of that. This is just great. Bacteria have hardly any unstructured proteins. And you think you're smarter than bacteria, so wouldn't you have more folded structures? It's the other way around. You have a much higher percentage of your proteins in unstructured states to start. And then they are more potent and powerful because each one of those unstructured proteins can bind to multiple targets. So the higher you are in the evolutionary hierarchy, the more complex organisms have the larger percentage of their proteins that are unfolded. And you may be surprised to find out that we now realize that 30 to 40% of your proteins are natively unstructured, at least to a certain extent. Maybe not the whole protein, but a significant part of the protein sequence is unstructured out of the ribosome. And that's so it can carry out multiple functions. So you remember the story about the 20,500 genes that you have? Well, we tell you now that as far as functional proteins go, you probably have at least 1 million functional proteins. And part of that is because any one of those gene products, any one of those proteins that you make, if it's unstructured to start with, can now act as multiple different proteins by forming different structures and interacting with lots of other things. So as far as functional states, functional proteins, you probably have a lot more than you realize. Question?
I was just going to ask, do you know what animal has the highest percentage of IUPs?
You. Humans. Humans have the largest percentage of IUPs of all the organisms. That's a good question. Probably chimpanzees right up there too, but us and the monkeys, we and the monkeys, we're good friends, right, evolutionarily. So anyway, pretty interesting story. So here's a couple of examples. The yellow part is the unstructured protein binding to a couple of domains there, and that's kind of nice, okay, and get the idea of other pictures. A lot of times unstructured proteins wrap around their target proteins. So in the red there is an unfolded protein that's now become structured anyway by binding to a target.